Hello, this is Dr. Bereng Askarian. I am an associate professor at Washington State University. I am also a professional engineer, a PE in the area of thermal fluids in the state of Washington. So this video is going to be about how to solve a simple ideal Rankine cycle using EES, Engineering Equation Solver. And eventually I'm going to post a video to show how you can solve the cycle, by hand using the steam tables, everything, the same. But this one is about how to, solve the cycle using EES. So before you watch this video, if you're familiar with EES, then you're fine. If not, there's a video I posted to show how to use EES for the first time if you have never used it before. And the link is in the description. You can find it there. Make sure you subscribe to this channel because I'm going to upload almost one video a day, but in the area of thermal fluids, fluid mechanics, heat transfer, thermodynamics, things like that. All right, so let's take a look at the Rankine cycle. Let's see how that works. Just write the equations and then write the equations for the efficiency at the end of it, how to calculate W dot from turbine, the power from the pump, everything, the TS diagram of it, and eventually how to calculate the efficiency of it. And then we want to see how we can write a beautiful code in EES to solve the whole cycle efficiently. All right, this is Rankine cycle. Rankine cycle is a power cycle, and the working fluid is steam. The idea when you say simple ideal Rankine cycle, we mean two things. There is no pressure loss in the turbine, in the boiler or in the condenser. There's no pressure loss. All the processes are reversible, and the pump and the turbine are isentropic. That's what we mean by the ideal simple Rankine cycle. When we say simple, it's because we don't have any reheat or regeneration. We don't have any open feed water heaters, closed feed water heaters. We don't have any of those. And in order to solve an ideal simple Rankine cycle, you only need 3 data points. And those 3 data points are usually the pressure and temperature at state 3 right before the turbine here, basically, and of course the pressure in the condenser. So if I know the pressure and temperature right before the turbine, pressure and temperature of the steam before the turbine, and the pressure or temperature in the condenser, I can solve the problems of P4, and this would be like P3 and T3. If I know these values, I can just solve the whole cycle. So let's just go through the cycle, see how that works. The way it works for the ideal Rankine cycle is it's like this, that first the fluid is at this state. Let's just start from the very beginning, and at this state as a compressed liquid. It's a compressed liquid, but it's like saturated liquid, which means that water, steam at this point, has a quality of 0. And because, there is no pressure loss in the condenser, P4 equals P1. And these two pressures are the same. So you have liquid water basically here. That's where the liquid water is. And it is saturated liquid, which means quality is 0. You send it through the pump, regular water pump, right, to increase the pressure of it. What happens when you increase the pressure of it? You are on the TS diagram. This is your TS diagram. Take a look at this TS diagram. On the TS diagram, you're jumping from one pressure level to another pressure level. Basically, this is one pressure level that we have. These are constant pressure lines, and you jump to the second pressure level, which is this one. You can go from, 20 kPa to 15 megapascals, or whatever the pump is doing, basically. So, and if you look at, these constant pressure lines, you can see that, okay, so I jumped from point 1 to point 2, but it is a straight line. It's a straight vertical line. Why is it a straight vertical line? Because this is supposed to be an isentropic pump. For an isentropic pump, basically S2 quality, here S2 equals S1. Like this. So it was an isentropic pump. That's constitutes these two, the pump and the turbine, are supposed to be isentropic because it's a simple ideal Rankine cycle. Okay, so that was the first, going from state 1 to state 2. What did we do? We had liquid water, which was saturated liquid, so quality was 0. Then went through the pump, and we knew the pressure of water before the pump, and the pump jumped it up to the second pressure level, second basically like the pressure line on the TS diagram, constant pressure line on the TS diagram. Now, here's the thing. In order to, you know from thermodynamics, in order to determine basically a state so you can solve problems, you need two independent properties. Question, do I have two independent properties at, point one? Yes, I do. I know the value of quality. Quality is supposed to be 0. X1 is 0. And I know the value of P1. Usually it's given. Why? Because P1 and P4 are supposed to be the same. If P4 is given, the pressure in the condenser is given, P1 is P4 because it's an ideal Rankine cycle. All right, so state one is determined. You have two independent properties, you know what's going on there. State two, because the process was isentropic, then the entropy of state two equals entropy of state one. So I know one property there. Also, because it's an ideal cycle, the value of pressure at 3 and pressure at 2 are the same because there is not supposed to be any pressure loss in the boiler. So first you go through the pump, isentropic pump, then so you have the value of also P2 because you know the value of P2 is actually the value of P3. So far, when the problem, the ideal Rankine cycle is given, you're only usually given only 3 properties. You are only given like P3 and T3 and maybe, P4, either P4, or T4, one of those, because it's enough. That's enough. So you have only 3 pieces of information, but you can solve the whole cycle. So now state 2 is determined because why? Because I know S2 is S1 and P2 is P3. So I have 2 independent properties. I can find all the properties of water in the steam tables or using EES, whatever I want to do. All right, so they send the water, which is still compressed liquid, judging by where it is on the TS diagram at point 2, you're in the compressed liquid area. And on that constant pressure line here, this is the constant pressure line, we start heating it up. We heat it up and eventually it goes through 2 phases like this, and eventually it becomes superheated vapor to point 3, this point 3. And the boiler gives it heat, so it becomes superheated vapor. Now it is ready to be sent through the turbine, and the turbine can produce work for us. Keep in mind that for the pump, we had to provide some work. We had to provide some pump work. Here, we can see it here. This is the pump work. And based on the pump work, whatever work we gave to the fluid, then we could increase the pressure up. Now it went through the boiler and reached state 3. I told you before that usually when it comes to Rankine cycle, P3 and T3 are given. So the state at point 3, which is a superheated vapor, is also given. You know what it is. You know these 2 values. Because you know these 2 values, you know the state of the fluid there. You can find other properties such as enthalpy, stuff like that, such as entropy, and you need entropy eventually. And so at point 4, because again, it's an isentropic turbine, it's a vertical line on the TS diagram, because S4 is supposed to be S3, like this, right? And as a result, you have S4 equals S3, and P4 was already given in the information, P4 or T4. And that means that this state 4 is also determined. So if I want to use EES for every single state, I have 2 independent properties, and I can find other properties such as entropy, such as enthalpy, if I need internal energy, if I need a specific volume, we don't need it for this case. But if you do need them, you can find all the properties because the states are determined. Why? Because at every state, I have 2 independent properties. All right, and finally, in the condenser, because the condenser is supposed to be a reversible process also somehow, and in the condenser, there's no pressure loss, so you can see that it's on the constant pressure line, a horizontal line. That's the constant pressure line, because under saturation dome, pressure and temperature are not independent, and that's why you get the horizontal line. And so you go from 4 to 1, and then the steam loses heat to river water or whatever the cooling mechanism that they have. And that constitutes Q out. This Q out, lowercase q out, is basically like the heat in the condenser per unit mass flow rate. And this is the heat from the boiler per unit mass flow rate. So in this process, what did I cover so far? What I covered here was the whole cycle, and the fact that it is an ideal cycle, every process is reversible, the turbine and the pump are isentropic, and there's no pressure loss in the boiler or the condenser. And if somebody tells you, hey, I have an ideal simple Rankine cycle, and you go ahead and solve it, the way to solve it is, okay, give me 3 pieces of information: pressure and temperature before the turbine and the pressure after the turbine. Oh, either pressure after turbine or the temperature after the turbine. Everything else you need to already know. That's enough to solve an ideal Rankine cycle, because once they say it's an ideal Rankine cycle, you know that there is no pressure loss. You know that state 1 has to be saturated liquid, quality is 0, all of those. All right. Now the question is, okay, what are we after? One question you might ask is, okay, so what is this good for? Well, it produces work. You take a look at this cycle. It's a clockwise cycle. You know that clockwise cycles are power cycles, and you can see that this area inside the TS diagram is an area that is basically going to be the net amount of work that you are going to get out of this turbine, out of the cycle, not out of the turbine, because the net amount of work is the work of the turbine minus the absolute value of the work of the pump. We're going to talk about that too. So now that was a general overview of the Rankine cycle. Now let's talk about the equations of it and how to calculate the efficiency of it, how to calculate the work of the turbine. And once we establish the equations, we have the right equations, we can type equations in EES and then solve the problem and get numbers. So I'm going to give you a problem that has numbers. I'm going to solve a problem from this book, Cengel's Thermodynamics book, example 10-1 from the 8th edition. So you see how that works. All right, this is the example that we're going to solve. This is example 10-1 from Cengel's Thermodynamics book, 8th edition. I can see that we have the numbers. Those two, P3 and T3 that I told you about are given, 3 megapascals and 350 Celsius. And then the pressure at the condenser is also given. At this point, I don't need any more information because I know it's an ideal simple Rankine cycle. So I know that, P2 is supposed to be the same value as P3. And I know the quality here is supposed to be 0 and this pressure is given. And of course, I know that pump is isentropic. So S2 is S1. And I know that the turbine is isentropic. So S4 is S3. And as a result, for every single state, I have 2 independent properties. And based on that, I can determine every single state. Next step is to apply the equations. The equations for this one is usually just the first law of thermodynamics and the second law of thermodynamics. I already applied the second law of thermodynamics for you, believe it or not. You're like, when did you apply it? I already did that. When I said the process is isentropic and S2 equals S1, or the turbine is isentropic and S4 is equals S3, that is the second law of thermodynamics. I don't need to get into it today, but when you say isentropic means adiabatic and reversible. Adiabatic and reversible, they basically, once you apply that to the second law of thermodynamics, that term S dot gen, entropy generation, becomes 0 because it's reversible, and all the heat transfer terms go to 0. And because a turbine or a pump is modeled as a steady state, the result of those assumptions, adiabatic and reversible, is the entropy should not change. And that's what the math will give us. So S2 equals S1, in fact, is the second law. I already applied it. And S4 equals S3 is also second law in this case. So what is left is just the first law for every one of these processes. We have 4 processes. We can apply the first law for all of them, and that's it. That's how you solve the whole cycle. So let's look at the equations that we need. We know we can find the properties because all the states are determined. So we're going to take a look at the equations we need to put in EES to solve the problem. All right, let's do this. So this is our cycle, same problem, right? Example 10-1 from Cengel's Thermodynamics book. Okay, let's see what we got. All right, first process, we know all the states are determined. At this point, we know that we can find all the properties. All right, so process 1 is 1 to 2 is the pump. Let's just write it down. So pump is process 1 to 2. Let's see what I have here. First, you write the first law of thermodynamics tells you second law that I already showed it to you. Second law says S2 equals S1. Okay, and the first law, what is the first law? First law, I have to just write the first law for this process, which is Q dot net minus W dot net plus M dot H1 minus H2 equals 0. H1 to H2, HR enthalpy. Oh, what happened to velocity and potential energy? And there's the change in potential energy and kinetic energy are definitely negligible, especially when it comes to when you have the change of enthalpy of liquid water. So that would be the case. Because the pump is isentropic, basically this Q dot net for the pump from 1 to 2 says W dot net from 1 to 2, right? And Q dot net would be 0 because it's isentropic, right? And when you calculate this whole process, you got to keep in mind that W dot net for the pump from 1 to 2, which is basically is the W dot of the pump, if you want to think about it, that is going to be less than 0. Because why? Because basically pumps actually consume energy. So you will see that the first law will give you. So that would be our first law. Okay, no problem. Let's take a look at the second process. Second process is the boiler. In the boiler, and we go from 2 to 3. Okay, what do we have here? You don't have to worry about the second line in this case. Let's just write the first law. First law for the boiler is Q dot of boiler, which is Q dot 1 to 2, basically, minus W dot net from not 1 to 2, 2 to 3, 2 to 3 plus M dot times H2 minus H3 equals 0, like this. Same case. That's the first one. All right, when you take a look at this boilers, we ignored all the losses, pressure losses in the boiler. So there is no power loss that you can apply like W dot net as power loss in there or something. So this term, because it's an ideal cycle, this is 0. So now I have the first law of thermodynamics for the boiler. And when you calculate this, definitely, in this case, Q dot boiler, when we write this equation in EES, Q dot boiler is definitely bigger than 0 because, of course, the working fluid is gaining some heat. So that's how you calculate, Q dot of boiler. Well, what about H2 and H3? Well, EES is going to give these values to us because why? Because all the states were determined. Every state had 2 independent properties. So that's how we're going to actually solve the problem. Just wait and see. The third process is the turbine, right? So the third process is the turbine. We just write turbine. Let's just write the second law. Second law, as I said, will tell you that S4 has to be S3. What about the first law? First law says Q dot net of the turbine from 3 to 4 minus W dot net of the turbine 3 to 4 like this plus M dot times H3 minus H4 equals 0 like this. Because the turbine is isentropic, Q dot net from 3 to 4 would be 0, and as a result you end up with negative W dot of turbine plus M dot times H3 minus H4 equals 0. For sure in this process, W dot of turbine is going to be bigger than 0 because it's supposed to produce work for us. Okay, if you want to calculate the efficiency of the system, actually you have enough information if you want to calculate the efficiency. But just because I want to, completely solve the problem, I can just, write this for the first law for the condenser too. If you write it for the condenser, the process, which is basically 4 to 1, based on this was turbine is 3 to 4, like this. 4 to 1, same case. You write the ideal, you write the first law of thermodynamics again. You don't write ideal gas law, just make sure you don't do that. It's steam, it's water. So Q dot first law, Q dot net from 4 to 1 minus W dot net from 4 to 1 plus M dot times H4 minus H1 equals 0. And of course, when you look at it this way, then because the condenser is supposed to be perfect, so there is no pressure loss in it, and condensers don't produce power, there's no power loss or anything in it, so this would be 0. And the only term that is left is just Q dot of the condenser. Q dot condenser plus m dot H4 minus H1 equals 0. Q dot of condenser is for sure going to be less than 0. Because why? Because the condenser, the fluid, the working fluid stream is losing, we're cooling it down. It's going to lose heat to the river water or whatever the cooling mechanism that we have. Now that we have all these values in every process we wrote the first law, we have Q dot for a boiler and condenser, we have W dot for the pump and the turbine, we have all of these values, you can actually find the efficiency of the cycle. The efficiency of the thermal efficiency of Rankine cycle is based on this definition. The definition is the desired form of energy, that's efficiency, over the energy spent to make the whole system work. The desired form of energy is the work that comes out of the turbine. However, the work that comes out of the turbine is not the only work that we have in the system. The pump actually consumes some power. So what they do is they're like W dot of turbine minus W dot of pump, like this, over Q dot of boiler. You might ask, okay, why did you use the absolute, sign here? Because W dot of pump is actually negative, right? I can write this like this too. Look at this. W dot of turbine plus W dot of pump and over Q dot of boiler. And I'll be fine. Why? Because the W dot of the pump is actually a negative sign and W dot of turbine is a positive sign and Q dot of boiler is a positive sign. So I'm going to get the same value. Depending on, how you are setting up your equations, you will see that in EES. Because this is an ideal cycle, let me just show you something very interesting. Look at this. Only and only, I'm going to just write it twice because for ideal cycle, because there are no losses in this case, you can also find the thermal efficiency as 1 minus Q dot of condenser, absolute value, because I want to make it positive, over Q dot of boiler. Only for the ideal case, and that comes from the first law of thermodynamics for a complete cycle, that these two values, you can also find this, you can find the efficiency of the cycle this way, but only for an ideal cycle. For a non-ideal cycle where you have pressure loss in the boiler or the condenser and heat loss in the piping system, in the boiler you can have, in the piping you can have heat loss before it reaches the turbine. That's not going to be the case. You can't write this. Take a look at this. I said only and only for ideal cycle. Like this definition, no matter what, if it's ideal cycle or non-ideal cycle, this definition is always correct. The desired form of energy, power, net, which is also can be written as W dot net like this. So you can either, write this as W dot net over Q dot boiler. This is good for non-ideal cycles too. But if it is an ideal cycle, you can also get the efficiency from this. Where does it come from? When you write the first law of thermodynamics for a complete cycle, then the first law can show you that this is working for only ideal cycles, not for non-ideal cycles. That's not usually the case. All right, cool. So now we have all the equations. Let's just take a look at what we have here. We solved the whole problem. At this point, you're like, okay, well, what do you mean we solved the whole problem? We have no numbers, nothing, right? So, well, we're going to put all these values in EES and see what happens. First, we're going to determine the states, every single state, state 1, 2, 3, 4, and find out the values of enthalpy and entropy, the values that actually we need. Once we have those, then we're going to just type the equations the way that I just wrote it here, and that's it. EES is going to give us all the values. And I'm going to assume the m dot is like 1 kilogram per second. So let's get started. Let's do EES. All right, here we are in EES. And I already, wrote some documentation, my name, Simple Ideal Rankine Cycle, example 10-1 from Cengel's Thermodynamics book. If you watch the video I posted for EES, the first step to solve these problems is to choose the unit system. That's very important. So we go to options and we choose the right unit system. The unit system I can use here is basically, I can go for megapascal. It's going to be okay for this case. I'll stick with kilopascals because we have 75 kPa, and I'm going to stick with kilojoules, and I can do Celsius. Question is that, well, do you have to go for basic science like Kelvin and joules and pascals? You can do that, and you can never go wrong with those, units. The reason that I can get away with like kPa and kilojoules in this problem is that if you remember the first law that I wrote for you, I ignored the changes in kinetic energy. So you did not have enthalpy and kinetic energy V squared over 2 in the same equation. If you have both of them in the same equation, you'd better go for basic SI units. Because if you have enthalpy in kilojoules per kilogram and you have velocity in meters per second, no, that's not going to work. You're going to get error messages, or you're going to get wrong numbers, and this is going to be bad, right? So if you have enthalpy and kinetic energy in the same equation, first law of thermodynamics, you'd better be sure that you're going to get some error messages if you pick kilojoules per kilogram for enthalpy. However, we didn't have that. We ignored the changes in kinetic energy and potential energy. Because of that, I can actually go for kilojoules, and as a result, all my powers are going to be in kilowatts, right? So you will see that. And I'm not dealing with ideal gas law or temperature in terms of Kelvin right in front of me in an equation, so I can get away with Celsius and I'll be fine, and I'm not gonna encounter any unit problems. That's the reason. So Celsius, let's do Celsius, kilojoules and kilopascals. These are good. So let's go for that. Okay. This is how I start writing a code. How many states do we have? We have 4 states. So let's get started. So I'm going to start with state 1, the one before the pump. State 1, documented. Okay, what do I have here? I have pressure and temperature, P1, and the way that I'm showing it, I'm going to use the something that is called the array table. So instead of P sub 1, underline 1, I'm going to use P bracket 1. So it's going to put it in nice tables for me. The what do we call it? The array table. These tables. These are the array table. This is parametric table. Array table. These are array table. It's gonna, both of them are parametric. This doesn't make sense. Anyways, you'll see. You'll see. Just wait. It's going to be fine. This is array table. This is array table. So it's going to show up in array table very nicely. So P1, the unit system I picked was, what was it? kPa. So P1 is 75 kPa. 75 kPa. Okay, cool. What else did I know about, state 1? I knew quality, X1. X1 is 0, right? Quality was 0. It was saturated liquid. All right, what else do I need there? I need 2 things. I need enthalpy and I need entropy. Why do I need entropy for? Because S2 is going to be S1, so I have to calculate S1. So first I calculate S1. S1 is the entropy of, what's the working fluid? It's steam. All right, P is P1 and quality X is X1. I talked about property indicators in the video. Again, if you're not familiar with these, go back and watch that video. It's in the description. Okay, S1, I got it. H1, I need H1. H1 is the enthalpy of steam. I can just be lazy and just copy this thing because it's the same problem, right? The same Control C and Control V here and just magic. So I have these 2. I got my state 1. It looks good to go. What do I do now? Writing the rest of the code? No, you don't do that. You just run it right now and fix the unit problems. Okay, let's see what I have. I don't get anything. Oh, I got something. This is my array table. So I have to fix it. Pressure is kPa, that's fine. Enthalpy, X doesn't have any unit, so quality doesn't have a unit. This one, so you have to just right click. You right click on H and the unit shows up. Because I chose kilojoule in my unit system, this would be kilojoules per kilogram. It's important. And quality for entropy, I chose kilojoules, so it would be kilojoules per kilogram dash Kelvin. That's what the unit is. And quality doesn't have a unit. You can save it and then go back to your code, basically. So that's what I'm going to do. Now it's good. There shouldn't be any unit problems or anything right now. Everything is taken care of. Let's do state 2. what do I know about state 2? State 2, I know that P2 is P3, right? And P3 was given. So P3 was given as, what was the value of P3? It was supposed to be 3 megapascals, if you remember the video. So it is 3 megapascals, is 3E3 kPa, because I have to be consistent with my unit system. 3 megapascals, 3,000 kilopascals. I have to be consistent. What is T3? T2 is not given. T2 is not given, but I know S2 is supposed to be S1, like this. So now I have two independent properties. I can calculate enthalpy at 3. So let's do that. Enthalpy at 2. H2 equals enthalpy of steam, well, where the entropy is S2 and pressure is P2, like this. Let me see if everything looks good. Yes, everything looks good. If you want to find the temperature there, you can, because somehow you might need it for the TS diagram. If you want to create the TS diagrams, that would be temperature. And I can just copy and paste this, Control C and Control V, and I should be good to go. That's it. So I have my state 2. State 2 is determined. What do? I just run it, see what happened. Okay, so I have this now. Oh, T is added to the, the array table. Right click on it. It's supposed to be based on my unit system. It's supposed to be Celsius. Fix it. Now you have Celsius here. So everything should be good. You can save it. You can save your code and keep going. All right. What's the next step here? Next step is state 3. State 3 is before the turbine. What information do I know? I have P3. P3 is given as 3E3 kPa, like this, and T3 was given as 350 Celsius. 350 Celsius. Okay, I got that. No problem. What do I need to find? I need to find entropy because I need it for S4 is S3. S3 is the entropy of steam. P is P3 and T is T3. Take a look at everything looks nice, good. And finally, I need H3 for my first law of thermodynamics. H3 is enthalpy. Okay, and I can just copy and paste this, Control C and Control V, like this. Let's take a look at it. S3 is entropy, steam, blah, blah, blah. All right, everything looks nice. What do? I run it. Let's run the values. Let's take a look at this. Yeah, you have basically the enthalpy. Yeah, the enthalpy before the turbine is the maximum, and it has to be. I mean, obviously, it's after the boiler. So if it's not like this, then something's wrong. Okay, we go back here, we ran it, and there's only one state left, and that's state 4. State 4. What do I know about state 4? About state 4, I know state 4, P4 is supposed to be P1 because it is an ideal Rankine cycle. So I don't need to even write anything, but I have to write it this way. And S4 is supposed to be S3, like this. Now I can calculate two things. Temperature at T3 is going to be basically temperature at T1. It's not going to be anything else. I guarantee at this point. So I could even calculate temperature here and say, okay, T1, because it's ideal. T1 is the value of temperature. You can add this to state 1, temperature of steam for these values, Control C and V, like this. So now you have the saturation temperature, and T4 will be for sure based on the fact that this is an ideal cycle. T1, you looked at the TS diagram, you know what I'm talking about. There is only one more thing I need to find, and that's H4. H4 I need. That would be enthalpy of steam, where pressure is P4 and S is S4. Looks nice. I guess I got everything right. So let's run it. Look at that. I got everything. If you want to find the quality, because you know it's two-phase here, you can add an equation and find the quality at X4. So that would be X4. X4 is the quality of steam, I can just copy and paste this because I have two independent properties, Control C and Control V, and this should give me the quality. And let's run it, see what we get. Quality is 88%. If you look at the thermodynamics book where they have the actual solution for this problem, then 88% is the quality of the steam for this case. All right, cool. Now, what's next? What's next is I got to apply the first law of thermodynamics for every process and calculate those values I wanted. So that's why I had that game plan. I wrote my equations. So I'm not going to haphazardly just type a bunch of equations. First, you have a game plan. Your unit system is fine. Everything looks good. You just type down your equations and you check that you have enough equations, enough unknowns, and you can solve the problem. And up to this point, you know, your code is solid. Doesn't have any errors, anything, right? So now here's the solution. Solution is, okay, so first let's just do the pump. Pump is the process from 1 to 2, right? So, and I need to calculate the work of the pump. That's important. All right, so pump is here. And let's write the first law of thermodynamics for the pump. I already wrote the second law in the states because I needed it. All right, so what's the first law of thermodynamics? The Q dot of the pump is 0. I don't need to write it. Negative W dot of the pump. Something I need to add to given values here at the before state 1, add this because we're doing this based on 1 kilogram per second per unit mass. That would be 1 kilograms per second, just to be consistent, because I'm going to use M dot in the first law of thermodynamics. So I added this line up there. All right, negative W dot of the pump, like this, W dot of the pump, plus M dot times H1 minus H2 equals 0. You can say 0 watts or 0, it's going to be okay. It's not going to cause a problem for you. So let's run it. Let's see what we get. You run it, you got this. Oh, this is the value. Question, what's the unit of W dot of pump? All right, my units were kilojoules, right? The first law, I have enthalpy in kilojoules per kilogram, and I have mass flow rate in kilograms per second. So this will be kilowatts. Be careful. So I'm going to just type here kilowatts, and you see, no unit problems. And as I told you before, W dot of pump is negative because pump is consuming energy. All right, cool. Pump is done. Done. Let's do the next one. Boiler. Boiler. Q dot of boiler. Q dot B, like this. Q dot boiler. Plus, there's no work in the boiler. Plus M dot times H2 minus H3 equals 0. That's the first law for the boiler. All right, let's see what happens here. Let's run it. I got Q dot of boiler. It would be the same thing. It would be watts, kilowatts, like that, right? Just like the same case before. Now, next one. Let's do turbine. See how easy it is? Turbine. And the negative work is isentropic, so there's no power, there's no heat loss in the turbine. So W dot of turbine, like this, plus M dot times H3 minus H4 equals 0. That's the first law for the turbine. You might ask, hey, what's the deal with W dots, negative W dots? Well, I just stuck with the basic form of the first law of thermodynamics. I don't mess with any of that. Just write the equation correctly. EES will give you the answer. Don't worry about moving things around. Just stick with the math. The math will solve the problem correctly for you. All right, let's do it one more time. All right, look at that. I got 713 kilowatts for power of the turbine. I got that value. And if I want to, at this point, I can calculate the efficiency of the system. But if I want to, I can calculate the, the heat loss in the condenser, which will be Q dot of condenser plus M dot times H4 going in minus H1 coming out equals 0. That would be the case. And that's the first law for the condenser. And this would be the condenser, kilowatts again. Of course, it has to be kilowatts. And of course, it is negative because the steam is losing heat to the river water. All right, now it comes down to, okay, how do I calculate the efficiency of the cycle? I'm going to calculate the efficiency using two different methods. So the efficiency is eta, right? Eta of the cycle, the efficiency, let's just efficiency like this, right? So eta of the cycle, I'm going to use two different methods. I'm going to use like eta thermal method one. Method one is finding the net power, right? Net power. So I'm going to type W dot net over Q dot of boiler, right? Well, the question, I didn't calculate W dot net, so I need to add one more line to the code, and W dot net would be basically W dot of turbine plus W dot of pump, like this. And you might ask, oh, why are you adding these up? You're adding the power from turbine to power from, pump. Well, the power of the pump is negative. So W dot net is all the works. You add them up. The math will take care of it, because W dot pump, if you stick with the basic form of the first law of thermodynamics, W dot pump turns out to be negative. So don't worry about it. The negative is inside this thing. Don't worry about it. Everything is good. Now I have the efficiency. Look at that. So I got the efficiency. 26% is the efficiency of it. I have a unit problem here, which is W dot net, which I have to fix, and the unit would be kilowatts. So this is my efficiency. I can highlight it, and that's the efficiency, 26%. Let's double check and see the thing I said about, the other equation for efficiency, that if it is an ideal cycle, it could work, right? Eta thermal 2. I said, if you have 1 minus Q dot of condenser, I have to use the absolute value for this one because it's a negative sign, and over Q dot of boiler, I should get the same value. Let's take a look at our formatted equations. This is our formatted equation. Very nice. Look at this. You have all the states, steam. I have the first law of thermodynamics for every process. That's beautiful. And then this is eta. This is supposed to give me the same value as this one. Because this is an ideal cycle, I am confident this is going to be the case. So I write for only, and only, one more time, for ideal simple Rankine cycle, not for the regular cycle that has losses and stuff. So only for this one, it should work. Let's run it. Let's see if I'm right or wrong. Look at that. Same value. That variable gives me the exact same value. So I saved it. So there you go. Now it looks good. So that was it. I just solved the problem. Just to double check our results, because this was an example from the book, Thermodynamics, Cengel. So what I'm going to do is I'm going to take a look at the book. I'm going to share the book with you, see what the book got. Did we get the correct answer or not? Let's just double check that. So this is Thermodynamics, the 8th edition, Cengel's book. This is the example that I just solved using EES. Take a look at all these values. They're the same values that I use, nothing different. But they use the steam tables. I can solve this problem using steam tables. That would be a different video. And they calculate the power of the pump because it was isentropic. It's a different story. So because of a liquid pump, they use a different equation. That would be another video that I make for you. Why did they use this equation? That'll be something else. But take a look at this. I got same value for quality, didn't I? I got 88.61%. That was something, wasn't it? I got 88.61 in my EES code. And so I can share my EES code. You can take a look at it right now. This is my EES code. Take a look at it. I got 88.61% for quality. And the book that solved this problem also got the same value, 88.61. Nice. And of course, if you look at the values of enthalpies that you got, I got the same values. Everything is the same. And the work of the pump, eventually they use the other equation, 1 minus Q out over Q in. They use this equation. However, this equation only works for again, as I told you, ideal cases. You can go for basically the W dot net over, and then 26% that we got, the book got 26%. So that's it. And I hope you got something out of this video, and so you can, solve problems like this. And let me show you one more thing. Next page of the book actually solved the problem using W net over QN, and they got 26%. Of course, they should have gotten it. So everything is cool. Everything is correct with our code. The next subject would be how do we plot like a TS diagram in EES? So that would be a different video. After I make that video, I put the the link of that in the description, so you can click on it and watch it. I'm going to use the same code basically. The reason I use actually array table was because I wanted to actually plot the TS diagram. That was the whole reason behind it. So I hope you liked this video, you got something out of it, and make sure to subscribe to this channel so you can get all these videos every day. Thank you very much. You have a wonderful day.